Hi, this is the Tempter podcast where we discuss the latest in embedded Linux, IoT, and other things we find interesting. Your hosts today are Kim Raj and Cliff Brake. Hello, Kim. How are you doing today?
Hey, Cliff. How are you? I'm doing fine.
Yeah, still
Getting
hanging out at home, I imagine.
Yes, indeed. I think not much has changed for me in terms of work environment because I'm pretty well set in remote work conditions. I have all my workflows optimized that way, but it's always two ways. So I have teams that always worked in offices and they don't anymore. So I'm on meetings and Zoom calls more than I used to be before.
Sure, yeah. I guess today we're going to talk about a project we did, and it's a embedded Linux system. It connects to a number of sensors and data collection devices, some over USB and some over other buses like OneWire. And then it aggregates this data, stores it, and then displays it. And the display can be on a local LCD touchscreen or remotely on the same network using a web browser. So it gives you kind of an overview of the device we're talking about today, and we're just going to talk over some of the experiences we had implementing this product.
Mm-hmm. Yeah, I think it will be interesting, to recount on all our learnings and perhaps share some of the good or bads as we go along. So, going to be an interesting session today. And what would be an appropriate way to kind of describe how we kind of start from inception, right? From design perspective. So, what would be the appropriate things that you'd like to cover from like what was our design considerations at the very beginning?
Yeah, that I guess one of the first things you think about is selecting hardware. Anytime we're running an advanced embedded system like this, Linux is pretty much a given these days. Collecting a lot of data, you're storing a lot of data, and you're processing a lot of data. So that pretty much puts you in the Linux bucket right away. So then the next decision is what type of CPU processing platform are you going to use? And most of our customers fall into two categories. Actually, there's three categories. Most of them use system on modules or SOMs, and this is a little printed circuit board where the CPU and the flash and RAM and sometimes a Wi-Fi chip and a power management are all on one board. And these allow you to get a product developed quickly without a lot of hardware effort. You can typically use a simple 4-layer baseboard. So that's by far what most of our customers use. And then at the other ends of the spectrum are full custom designs where they do a full custom printed circuit board and they put down the chip and the RAM and the flash separately. So these take considerably more effort. There's considerably more risk. Typically more things go wrong. So, the SOM approach really really moves you forward quickly, and they do a lot of the heavy lifting for you. And then at the other end of the spectrum, we have single board computers where you take it would be more like a Raspberry Pi or something where the complete system is on one board, and you typically don't add a lot of custom circuitry, or at the minimum, you may add a simple expansion board on an expansion connector. The Raspberry Pi Foundation calls those hats. I sometimes forget between Arduino and Raspberry Pis. But anyway, so that's kind of the spectrum. So in this case, the customer really wanted to minimize their hardware design efforts, and they wanted to go with the SBC route. So that pretty much put us in the Raspberry Pi or other systems like that. So that's kind of where we got started with Linux and an SBC. So
Right. So given that like SBCs is kind of a good choice in this regard, there are several SBCs choices that are available, and I think we went through similar iterations of looking at what different SBCs would offer. And so could you recount on some of the design decisions that, or various SBCs that we kind of discussed and looked at, um, and what were some of their positives and negatives?
Yeah, the Raspberry Pi is by far the most popular, so that's obviously the first one we looked at. But in this case, the customer wanted 2 GB of RAM, so that kind of threw out the Raspberry Pi 3 at the time. And as far as platforms, like the Intel Atom platform and the x86 class are usually quite a bit more expensive and use a lot more power. So we ended up looking for platforms that were like a Raspberry Pi, but we could get 2 GB of RAM. And that's kind of where we ended up with the Odroid-C2.
Yeah.
And there's other ones out there as well, but at that time, it's where we ended up with. I know the Raspberry Pi 4 has lots of RAM now too, so that's changed since then.
Hmm. And I think the USB was another aspect that I think it has a lot more USB ports that we were looking for as well. So a few other things from software aspect that I was keen on was essentially the BSP support, because we were trying to use this embedded Linux, and we work with Open Embedded quite a bit. So obviously having some pre-existing support for Open Embedded was one qualification criteria, which pretty much now a lot of SBCs already do have their board support package layers. And and the other aspect that I think we looked at was how well it is supported in its community. And Odroid does have a Odroid forum, which is quite active if you look at it. So that's quite positive to have looked at that, that sense of support, that when you're going into such a design, there will be issues that, you always look for some support that you can reach out to community and people and discuss your issues and find few solutions. So I think that's quite important, I think, from my aspect as well, from software design point of view, that we are selecting a ecosystem.
Yeah, that's an excellent point, because you'll always run into problems and you'll typically need some level of support or software updates. And often if you simply update to the latest sources for an actively maintained product, oftentimes problems are fixed, and that can be a huge advantage.
Right. Yeah, I think the life cycle of products is also important in many cases. When you have a connected device that has to live in the field for longer, you would be invariably asked to do security updates, or CVEs, and all those things will come during the development cycles, and maybe some new feature work might evolve as the use case develops. And it might happen that you basically are in need of upgrading maybe kernel, or upgrading maybe base Linux system on it, because you want to support a new use case. So it's important from that aspect as well, that it's not like once designed, ship forever situation where the device will never get a software update, and you design the software, design the hardware, and that's pretty much it. So I think that new consideration of this connected maintenance is also a consideration, I think, that we have to make sure that we are dipping into a flowing river.
That's, I'll call that takeaway number one. Make sure you're working with technology that's actively maintained, because things change, requirements change. With a very capable system like this, there'll always be new features you'll add, because really you can do anything with it. So there'll be things you never anticipated will be done in the future. So that's important.
Mm-hmm. Yeah, so I think one of the things that I learned quite a bit in this was the watchdog and the RTCs, the selection and how that was. And I've done watchdog work in the past, a little bit here and there, but I learned a lot about what all watchdog can do, and how important it is to have this early on supported on platforms. So what was your experience of this? I know that you've done a lot more in this area, but What was some of your challenges when it came to peripherals and other devices that were on the SBC, or we were planning to put on the SBC?
Yeah, Odroid provides a RTC module and an LCD module that we used, and they're just off-the-shelf devices that you can plug in. And all that worked pretty well, I think. The LCD is a 480 by 320 resistive touch LCD, so it's a tiny little thing, but it worked out okay. And the C2 chip, or at least the SBC, the Odroid-C2 doesn't have a SPI port on it. And most of these low-end LCDs that you would plug onto a Raspberry Pi or a similar SBC use the SPI port to drive the LCD. So in this case, the Odroid folks, they implemented their own LCD module, and it's just a parallel GPIO bit banged interface. And originally I was horrified by this, but it actually works out okay, or at least it performs adequately. The driver maintenance has been kind of a problem, and you've done most of that. What were the issues with that? I'm trying to think back.
Yeah, I think this is supported, the board is supported really well upstream, and I think Amlogic, which is basically the SOC provider for this SVC, has done really good work in upstreaming all their changes, over a period of time into kernel as well as U-boot and other places. So you could basically build mainline kernel today for Odroid-C2. However, when it comes to the SBC and the devices and peripherals that we need on this one, LCD was kind of one driver that was never upstreamed, and I think the reason was that I talked to the maintainers as well, and they said that the way it is written, it has to be done differently for it to be upstreamed. And so essentially, I think that was a hold off. So we never got to forward port it to, in more modern kernel, other than the vendor kernel. Vendor is here being Odroid. And so I think that was kind of a letdown from driver support point of view, but for what it did, it works pretty well with the kernel that it supports. So I think from product point of view, it came out to be fine. But I think when we talk about like future maintenance and things, I think there was additional work that we had to put into that one in order for us to upstream that. That hasn't been done so far. But yeah, I think that was a bit of a headache for us.
Mm-hmm. Yeah, peripherals can really have a big impact on a product, so it's important to consider that. Do you remember when you did a lot of the original software bring up? Does anything stand out in your mind of things we ran into? Or
yeah, let me think. I think so. Bring up essentially, initially booting up the device and all that went very smoothly to a certain extent. What we have to do was, because it was using 3.14 kernel, I believe, and at that point of time, and we were trying to use more modern version of Yocto, and so there were few new syscalls that a lot of packages were depending on, and it has newer compilers. So one of the things that initially I had to do was backport few patches into the kernel, or write few more patches that made it compile with the newer compilers. And same was required for U-boot as well. And Odroid upstream accepted all those patches. So at this point, I think all our changes are already upstream there. Then there was actually one issue that we found when we were bringing up Qt libraries and Qt-based displays on it. And we were using a version of Qt that was depending upon, I think, rename at syscalls, and these calls were not available in that kernel. So I spent quite a bit of time banging my head saying, why it doesn't come up? And so with a bit of debugging, figured that out. And eventually the fixes were basically in Qt not let it kind of assume that, and that made us move forward. And the other issues, I think we ran into, or at least initially I found, were how U-boot and how the whole boot process was set up on this one took a bit of understanding how it is all laid out. and
Mm-hmm.
it's a bit of learning there. For it's not as simple as you have on, say, Raspberry Pi, where you have your boot ROM booting you into a SD card, VFAT partition where your bootloader and stuff is. So here you had like all the BL1, BL2, that kind of booting process, which is kind of well set in the ARM world these days, but it's a bit of learning at the beginning. So
Mm-hmm.
once we figured that out, I think the other issue was that the U-boot basically have to be signed, in a way that they have scripts you have to run through those. So you just can't build any U-boot and throw it there. So there were a few things that we have to look through. But I think I must say that I was able to get all that information off of the forums. So it wasn't at any point of time that we were stuck. We were figuring out the information. The forum was also helpful to answer our questions in many cases. And yeah, so I think one of the cases I made there was, hey, we are on a very old kernel, and so there was some work happening to move to 3.16 kernel, which was kind of also used in Ubuntu at that point of time, and I think it is still supported. I believe 3.16 is still a LTS kernel, and so we then moved to that kernel after our initial port, and we got all our rename at and all the syscalls. So yeah, I think the other aspect where we spent a bit of time was when we tried to bring up the browser. And Qt has many knobs basically to enable touch screens and orientation and keyboard and things like that. So key inputs. So it took a bit of time for us to find the right combinations that we need for proper orientation. What all options and devices to enable in Qt access the touchscreen. And I think we also had few race conditions, I remember, where we were basically, do you remember that, where we were kind of launching the browser ahead of our application? And I think there were a few issues where we ran into where systemd wasn't finding the application. But those were like usual day-to-day kind of activities we ran into eventually. But
Mm-hmm.
these are a few things that come to my mind. Yeah.
Yeah, I think that's a good summary. One of the issues that we ran into at some point was when we were doing reboot cycle testing, which I'll just mention what that is. One of the stressful things a system like this does is just booting, because there's a lot of things happening, and if there's an instability in the system, oftentimes we'll find it during reboot cycle testing, is what I call it, and that's just simply a test where the system boots, and there's an init script that waits 30 seconds and then executes a reboot command, and it just keeps doing this, and then we have a counter that counts how many boot cycles. And it's been amazing the number of projects I've worked on. When we start this reboot cycle testing, we'll find problems, and we'll often run these tests at elevated temperatures and other extreme conditions.
Mm-hmm.
And on this product, one issue we discovered was about every 100 boots, the kernel would crash on boot up. And these are kind of the very difficult problems that you can't reproduce. And you get a very cryptic kernel stack trace. And you don't have the budget to throw the resources you need at a problem like this. So what we ended up doing was implementing a watchdog, hardware watchdog in the system, so that if the system ever locked up, it would just simply be rebooted or reset. So that situation is not ideal, but pragmatically, we could spend weeks debugging this problem that we could hardly ever reproduce, or we could throw a watchdog at it, and the 0.05% times it didn't boot properly, it would just simply be reset and it would get restarted. So that's just an example of the type of trade-offs we deal with during product development,
Mm-hmm.
where you have a small team, you don't have infinite resources, and you need to find solutions to problems.
Mm-hmm. Yeah, I think that was actually reminded me of a good um, watchdog issues that or rather the reboot issues. And I think we figured that if we inserted a certain USB devices, that's when this was more prominent. And I think we chased it down to the USB subsystem to a certain level. I think it was also related to the eMMC driver layer, I believe, at a certain point of time, where it would just not, I think, read the proper values. Perhaps I think we never got to the root cause in the kernel itself. But can you expand a little bit on the watchdog implementation? How did we go about it, and where all did we end up using it in the end?
Yeah. So anytime you deal with the system booting, there's multiple pieces of software that run. You typically have a bootloader in ROM that loads first and second stage bootloaders out of flash, and typically U-boot is called your second stage bootloader. And then U-boot loads the kernel, and then the kernel mounts the rootfs and hands off to the init system, which in this case was systemd.
Mm-hmm.
And if you want to protect the entire boot cycle from any type of problem, you need to enable the watchdog as early as possible and then keep it enabled throughout the boot process. So when we first approached this, we enabled it in U-boot and resumed our testing, but we discovered that we still had failures. So then we discovered that when the kernel initialized hardware, it was disabling the watchdog because the driver would initialize the registers for the watchdog timer.
Right.
And by default, the kernel doesn't enable the watchdog. That needs to be enabled in user space. So we patched the kernel to enable the watchdog when the driver loaded. So then we had the watchdog was on the whole time the kernel was booting, and then once the init system loaded systemd, then at some point you need to start petting the dog, as we call it. In other words, the watchdog needs to be serviced or else it will time out and then reset the system. So I think this watchdog had a timeout of 60 seconds or something pretty long that allowed us to get the system booted. And then at that point, systemd has support for watchdogs, and with a patch to systemd, we could enable the watchdog in the config. There's a runtime watchdog second and a shutdown watchdog second config variables that can be set. So we set the runtime watchdog second to 20, and which I think means that it pets the dog every 20 seconds, and then the shutdown watchdog second, that's the timeout. So that all worked pretty well once we took care of every part of the boot sequence. Then it was reliable after that point. So that worked out good. It was a relatively simple change, and it solved our problems.
Right. Yeah. I think one thing that you have is a peace of mind that your system, if it is remote, it will not lock up, and you'll have to pay a visit just to restart it. And I think it's important to have this put in early in design. So the other thing I think we kind of moving on from here was the decision between the file system layout. And I think we debated whether we should be doing a single copy or should be doing the double copy, or also called like the flip-flop A and B, what have you, as rootfs. So I think this also ties in with what kind of requirements the device has in terms of, or what do they expect in terms of failure rates and things like that. But I know that after a bit of deliberation, we went with flip-flop rootfs and read-only rootfs with flip-flop kind of rootfs partitions. And I think initially, it sounds pretty neat from concepts, right? That, hey, I got two rootfs there. If one goes bad, it goes to the second one, and then I'm up, and then I can repair the first one, and then vice versa. So what has been your learnings from this experience? So I think I'll share mine after you.
Yeah, I'll probably start to sound like a broken record here on the update issues or the update architecture, but most systems we've implemented have been a single rootfs with a updater embedded in an init ramfs in the kernel. And that has been astoundingly successful and very reliable.
Hmm.
And it has worked very well. So it's what I recommend, but some people are a little more conservative and they feel like, well, what if the rootfs gets corrupted, or what if we need to
Hmm.
roll back? And that was the case on this project. So we went ahead and did it. And again, when you're dealing with booting, anything that changes the boot, you have to touch every piece. So you have to touch the bootloader, and you have to touch the kernel, and you have to touch the user space where you're doing the updates. And I guess one thing that always kind of amazes me about Linux systems are they are astoundingly reliable. And unless you have a lot of resources to implement a flip-flop rootfs update system, the base system will probably be more reliable than
Yeah.
your mechanism to update it. So, in my experience, if you can keep the update mechanism as simple as possible, that will actually lead to a more reliable system than if you try to
Hmm.
make it super fancy with lots of safeties and fallbacks. And because one of the
Yeah.
problems with the fallbacks or the rollbacks or the recoveries, it's pretty tricky logic to implement. And if you're doing it from scratch, it's a huge task. I know there's various projects that are coming out that solve this problem, and hopefully one of those will be a good solution at some point. But it's not a simple problem. It's the second one we've done, and it kind of was the same experience. So yeah,
Very true.
what's your thoughts on that, Kim, after going through it?
Yeah. So I've seen it in large deployments, before like OTAs existed. People kind of resorted to this mechanism. And I think more than anything, it's just that people come from this background, they've done it in the past, and they think, they can do it again. But it's like, you're running on a hamster wheel. What I realized was, remember we did this logic in the bootloader to basically flip. And in the good case, it works fine, right? So you have your system is working fine, and you get a new update, you flash it, and then you basically call the fw setenv, and off you go. You knock the device over, it boots into your new rootfs. But the failure cases are really tricky. And, say you boot it into a bad one, and then now you have to, encode the logic to detect that condition in the bootloader, firstly, that you are now booting into a bad rootfs. So what is a bad rootfs, right? So it could be a simple one where you say, okay, the watchdog is not being serviced, right? So it's rebooting the device. And I think that's a simple problem because you can detect that. But in many cases, it could be also that, there are other aspects of the device that is freezing it. And so you have to now consider that, is there a condition that can happen that watchdog would not cover for? And secondly, you have to also consider the complexity of the logic in your bootloader, where you are basically saying, okay, I'll let it boot 3 times, and then fourth time I'll say, okay, you've been booting within 60 seconds, and I think you have a bad active rootfs. I'm switching you, and that's not something. It's not an easy logic for bootloaders. And given all these states that you have to maintain, it becomes pretty cumbersome and very error prone. And I think I believe in simplicity quite a bit, and I think it's no way a simple system to implement. So I understand that it solves certain issues where people want to be up in the service before they could kind of recover. But then I've seen the cases where people have a B system and then they have a CD system. So they have something called, disaster recovery partition, and then they have a primary disaster recovery and a secondary disaster recovery, and then they have a primary rootfs and secondary rootfs. So there is no end to it.
Yeah, yeah.
So the reason is because they forgot to take care of some condition, and now they say, okay, why not create another, a layer and another and another. So I think it's broken by design at that point. And I think the other aspect was we chose the rootfs to be read only. And I think while our expectations, and I think especially me, was that it would perform better. And because one of the things is that these devices, they boot off SD cards, and SD cards may have certain limited life cycles. So we thought that, if we do a read-only rootfs, then we could prolong the life of the SD card. And in certain cases, they tend to perform better too, because, it's in a read-only mode, and so caches are used better. But I think when we started to implement it, especially with systemd in picture, systemd has certain files that it always expects to write to. So we learned hard way that, /var/lib has to be read-write. Otherwise, your system won't boot. So my experience was that turning that read-only rootfs was easy, but debugging it and making sure that it worked reliably was quite an uphill battle as well. So I think we perhaps can do better with partitioning if we have to do, and I really think that we perhaps might say that, say, /var is going to be read-write, so therefore it can be mounted elsewhere, and rest of the rootfs should be mounted read-only. But I think this is something that if you are deciding to do a read-only rootfs, be prepared to account for these kind of issues where applications won't behave. You might have to go and debug them because a certain file they expect to write to is not available anymore, so they can't take the lock or what have you, and the application dies on you. Yeah, so I think those were like interesting learnings moving forward. If you were to ask me, would you do a read-only rootfs? I would say, do I have to? Then I will. Otherwise, I won't.
Yeah, that when you're putting systems in place like this, what you're essentially saying is that my application is more reliable than the base system. So you're saying that my application is more reliable than Linux file systems. And these mechanisms are certainly justified in some scenarios, maybe extremely remote, unattended devices. But they really slow you down, so there is a cost. It's not free.
Yeah.
And anytime you add complexity to the system software, I've lost track of the number of times where we've had to move files from Etsy in different places into the data partition. And Open Embedded has some really nice mechanisms to do that and manage it. So there's definitely support there in the tooling. But it's just that over and over you're running into these files that need to be written to, whether it be Etsy local time or networking config files, or the list just goes on and on.
Yeah.
Pretty soon you put the entire Etsy in the data partition, but then what happens when you update the system and something got changed, but you still have an old copy, and it's just not a very good policy to take a snapshot of all of Etsy and then just blindly use that on top of a new rootfs. It definitely has its problems, and people need to be aware that there is a cost.
True, very true. And I think, moving forward, I'm interested in Delta updates, and perhaps those are also interesting from that aspect, that if somebody has limited kind of network bandwidth, that they can deliver the payloads to the system, things like OS3 and other Delta update mechanisms. I think they are interesting technologies that are upcoming.
Yeah, certainly.
And cool. So now we have talked about our system design. Let's kind of talk a little bit about our application design, and what were our considerations there. And I know Cliff, if it is Cliff, it has to be Golang. So why don't you go ahead and talk about the application design aspects, features, etc.
Yeah, this system needed to process a lot of data, store a lot of data, and then display it over a web user interface. So that's really an application type where Golang, or Go if I want to say it correctly, excels. So we implemented a web UI in the application that was displayed locally on the LCD using a browser. And for the browser, we use Qt WebEngine, which turned out to work pretty well. There's some disadvantages to that. It's quite big because it uses the Chromium engine. It's pretty difficult to compile. You need gobs of RAM, but in the end, it worked out fine, and it works nice. The web UI on the little tiny quarter VGA display is quite responsive, and it looks nice and it works well. So that all did good.
Mm-hmm.
And then once we needed a way to store all this sensor data, and it's essentially time series data. It's basically a bunch of data collected over time. And we ended up going with InfluxDB, which is a time series database written in Go. And it turns out it runs just fine on these SBCs, and it is very efficient at storing data and retrieving it quickly, time series data that is. So that worked out well. And then early on, I guess we still have it there, but we also put Grafana, which is another Go application, on the device to actually provide a way for remote users to view the data. And we've eventually put graphing right in the application, but early on it was nice to have a way to view our data easily and basically build any type of dashboard we wanted during the engineering phases. So if you're dealing with sensor data, I highly recommend InfluxDB and Grafana. It can run on a server or an edge device, so it's a very versatile set of tools.
Yeah, and I think some of the aspects of the applications, I think it's important to also see that the web UI framework we had on the system was very efficient, actually. And I think I was surprised to see, given that it was bit banging on GPIOs and how responsive the UI was, it was kind of quite satisfying in the end to see it work so well. And I think, we do have some aspects. You remember we were trying to see whether we can have a keyboard on the UI, and because it was a touch screen and we had like a pen that we could use to type in, and we're trying to look for some keyboard integration, some like virtual keyboard integrations and things like that. And so I think that was kind of a good requirement from UI aspect. But other than that, I think it really worked well for us. And I think other thing that I'm remembering now is our updater that we wrote in Go in our application itself. We had few issues with corrupted updates. And do you remember what we did there? And did we kind of figure out what was happening and why it was doing so?
Yeah, it seemed to be a sequencing issue. Once again, it was a subtle issue that it was difficult to debug that we wouldn't have had if we'd used our traditional update technology. But yeah, the nice thing about a flip-flop rootfs is you can actually write the update logic right in the main rootfs, because you're not running from the rootfs you're updating. So that part's actually kind of neat. But
all right, so I think the one other aspect we followed on this one was our release mechanism, and I think I really liked the Semver mechanism that we introduced in there. So, and I know that you do the releases most of the time. So, would you want to cover that up for how the release model works here?
Yeah, we pretty much use open embedded, just kind of the way it is. We have recipes that build our applications and all of our custom pieces. So it's pretty much a one command build, one run command. It fetches the latest application sources, builds everything, and then outputs an update image that we can put on a USB disk and then update the system or upload to it, over the air or whatever. So yeah, that's one of the things that I always insist on, is we have to have a really clean build and build and release process.
Yeah, I think the way we kind of also prepare the changelog for the end user is also interesting. I think I really like the method you used to use the changelog from, I think it's called changelog or and
Yeah,
I kind of
keep a change log, I
keep
think.
it
Is that
change.
is
Yeah,
that the
keep it.
website?
Yes, keep a change log. Yeah.
Yeah, I highly
Um,
recommend that site for anybody interested in release management.
mhm,
Um,
mhm.
the basic premise is you want to manually construct a change log for your end users because they're not interested in a Git history, which we can easily do that with Git submodules. We could
Mhm,
easily generate a Git change log between every release, and we've actually done that on other projects.
mhm.
But the premise of a manually generated change log is there's succinct entries in it that are easily understandable by end users. And
Right.
the process is anytime anybody on the project makes a change that gets pushed in for release, they update a change log. And there's the next section. So
Mhm.
and then that list of changes is what gets sent out with the release.
Yeah. Yeah. I think it's a really good mechanism to communicate the changes in a more like human readable format. So.
Mm-hmm.
Uh, all right. So I think that perhaps covers the topic that we had for today. We would probably talk about why we did SE Linux in there, maybe in some other episode. But
Yeah, I forgot about that. Yeah, that was another complexity that definitely took effort, cost us
yeah,
time, and yeah.
yeah.
Well,
Anyway, so
one
it
other
was
thing that just crossed my mind is, we use Qt WebEngine for this project, but I know you've been working on some Qt WebKit stuff, and that's going to be in future releases of Yo, and I think you've already put it there, but maybe we could do an episode on that in the future and some of the
yeah,
advantages of that technology.
yeah, yeah. Certainly, I think that'll be awesome. So I've been playing with it recently, and it's been turning out to be good. And it does have a virtual keyboard, and I think
Mm-hmm.
we'll do a write-up as well with some screenshots and show a kind of a kiosk image with the Yo running on Raspberry Pi using Wayland, and that works pretty well. And I think I'm pleasantly surprised. It's small compared to other browsers in size, and it has a little browser called so that browser can basically launch WP with a URL. So I think pretty neat. You can run it in a windowed mode. You can run it in full screen mode. So
Mm-hmm.
works with the EagleFS, works on Wayland. So I think it covers most of the use cases we have. So it'll be interesting to see. I think I'm looking forward to put it into a real product at some point of time. Maybe one of your future ones.
Yeah, that I'm looking forward to using that as well. So yeah, sounds good. Well, anything else today, Kim?
I think that's pretty much it. Thank you very much, and it was fun discussing this today.
Okay, yeah, same here. And feedback or suggestions are always welcome. So until next time, take care.